This talk is brought to you by the Bamberg Mathematical Consciousness Science Initiative.
Okay, great. Well, thanks again to Johannes and the organizers for this workshop. It's a great topic, and I did take a straightforward approach, just answering the questions that were the topics of the workshop. I should maybe put in front of this my take on what it is, how to do it, and where things stand. And I realized I'm not saying much about this middle one, at least not in terms of a dedicated section of slides. So I put this one in parentheses, although I will say a little bit about it as we go through. So yeah, my take on these questions. And so just by way of introduction, I'm going to try and keep things pretty high level. I've thought a lot about these questions. And so I'm going to give you a lot of pointers to things. And then hopefully I'll try to leave a little more than 15 minutes for discussion. Um, and then I don't know, the structure is such that we'll be done in an hour, right, Johannes? Because I definitely want to go to Mark's talk after it.
Exactly,
I'm
yeah.
going to be, okay, great. I'll be teeing Mark up. We have some minor possible disagreements, so add a little spice to the mix. Hopefully make that a little more interesting. And I'll say a little bit about those. And then Mark will have the last word. Okay, so first the question of what it is. So my take on that question is that it's a form of applied mathematics. So, you have mathematical biology, mathematical chemistry, and you've got mathematical phenomenology. And when you do that, you're expressing phenomenological claims using mathematical concepts. So just as you would in any applied area. So in a way, you do it the same way you do it anywhere. You take some first order theory and then you express it in a mathematical language. This has many virtues. It facilitates precision, pardon the typo, clarity, and communicability. And this is taken from Mark's slide without attribution, although I'm doing it out loud now. So I think we see it similar that way. And so it's great. It's helpful. It allows us to say things we couldn't really say if we were limited to verbal communication. And Husserl actually talks about this, and I will be focusing mostly on Husserlian phenomenology, although I'll say a little bit about a broader purview for that at the end. And Husserl actually says a lot about this. He says mathematics is a kind of necessary artifice for finite beings. An infinite being, a divine being, might not need mathematics. They could just think everything needed. But for us, we need calculation procedures and algorithms and concepts to allow us to access things, to be able to do something like compute the square root of 127 or take 35 to the 18th power or something. Now, an important kind of caveat here is that Husserl seems quite hostile to mathematics at times, famously in The Crisis, but he says things throughout his corpus that suggests that we shouldn't conflate mathematics with phenomenology. He says phenomenology is not an exact discipline. He says deductive theorizing is excluded from pure phenomenology. And this was sort of resolving these tensions because he says these things that are critical, but at the same time, he seems to use mathematics in phenomenology. And indeed, he was a mathematician by training. And so this paper, which is now almost 20 years old, it's hard to believe, was intended to resolve some of those tensions, to address them. And so it's easy to find online. I think I have a preprint on my website now. And I kind of go through all the things he says that seem against mathematical methods in phenomenology and show how they're not really in tension. And the basic idea across all of those is that you can't just sort of import phenomenology or mathematics wholesale into your phenomenological descriptions. You can't just assume the truth of some theorem of mathematics any more than you can assume the truth of neuroscience as the causal basis of consciousness or some rationalist kind of divine cosmology, nothing. You're just supposed to describe things as they appear, as they're given, and not allow these other extra phenomenological ideas to influence you and bias you. But, in the case of mathematics in particular, if you've gone to the effort to justify the mathematics you use, and if you're applying it in a way where the basic application kind of makes immediate sense, then I think he would say it is acceptable, and indeed he does things like this, as we'll see. So now, what exactly is involved when you mathematize something, when you formalize something? I mean, broadly speaking, now there's a question of what mathematics is, but certainly symbols are involved, and we want to distinguish the symbols from what you're applying them to. So you've got the symbols for the biological process, and you have the biological process itself, and there's some mapping between these two domains. And here, we mentioned this a little just now, and I think the next, what are these called? Sprint will be maybe on this topic, but there is this area called measurement theory, which I think comes pretty close to working out how this ought to work, the formal details of it. Measurement theory is maybe familiar to you via things like scales of measurement. So like ordinal scales, numerical scales, like rational and interval scales. And they say things like, depending, like if you have a set of numbers and they're just like the corresponding to, they're labeling football players or soccer players, then addition is not defined. You can't talk about player 5 plus player 7. And if you have just an ordinal scale, then certain operations are and aren't allowed. Different statistical measures are or aren't allowed depending on what measurement you're using. And so it goes to a lot of trouble to formalize all that. Now, Johannes and I have tried to sort of look at this more carefully, look at the literature, because a lot of this came out like in the last, starting in the 50s. It was very big at UC Irvine for a time, mathematical behavioral science, and there's people who still work on it. But we looked at the literature, and it gets pretty complicated pretty quick when you try and use it in a more robust way. But this is where I think there's a lot of promise in terms of really cashing this out. But that's to be seen. Okay, so I'm going to distinguish two kinds of mathematical phenomenology, and I'm using this typical analytic philosopher's crutch of type 1 and type 2. I think there's maybe better terms, but I'm going to start with these for now. And type 1 would be you're just using the mathematics to illuminate the phenomenology itself, right? You're doing the brackets of reduction remain. You're just trying to describe things as they're given, and the mathematics helps you do that in a relatively precise and communicable way. Type 2 is when you're using the mathematics not just to make sense of the phenomenology, but to highlight like links, isomorphisms, maybe structural invariants between neuroscience and cognitive science and phenomenology, sort of to help understand what are the neural correlates of the phenomenological structures you're looking at. And type 1 often can serve in this role, but there's a different intent, right? So someone doing type 2 mathematical phenomenology might be explicit, like have a starting point in, say, active inference and describe a mathematical model of time consciousness, say, that is directly using concepts from predictive processing or active inference, and that the idea of linking to that as the linking between physical systems that instantiate phenomenology and the phenomenology itself is part of the motivation for introducing it. And so this is a slightly different use. It's a difference in intent, and there's going to be a lot of interesting questions, I think, later about this. Now, I'm tempted to call these pure mathematical phenomenology and applied mathematical phenomenology. Those terms don't quite work because even in this first one, we're applying the math to the phenomenology. So I just wasn't quite sure what the best way to label these is. So again, I just called them type 1 and type 2. And I'll be considering both, but focusing, I guess, on type 1 here. There is a third meaning of this term, mathematical phenomenology. This could be understood as a kind of the phenomenology of mathematics, right? So how are numerical structures, geometrical objects, even things like algorithms, how are those given to the mind? How are those constituted in conscious processes? And this is well known as a project of Husserl's. I say early career, but it was a preoccupation throughout his career, but it was prominent early on, famously with the philosophy of arithmetic, the early lectures on logic, and in the logical investigations, but later in things like formal and transcendental logic. And I'm not going to focus much on this, although it's in the background. This sort of the things he says about this kind of make sense of how he both is, he says we should be cautious about about mathematics in any area, but also it's essential. This is the stuff I use to resolve those tensions I mentioned earlier. And the basic idea in a lot of this is like, look, again, it's this necessary calculus, this necessary, what's the word I'm looking for? Heuristic artifice. It's a necessary artifice, I think is the word he uses, for reasoning about anything that kind of transcends the immediate limits of memory and so forth. But if you let the mathematics kind of become a thing in itself, if you let that become the reality, if nature becomes a mathematical manifold, as he says later, and you're just working just from the math and losing sight of its application to your domain of interest, then it becomes a problem. And so we need to use it, but we need to be careful when we do use it. Now, I believe Professor Hartimo is giving a talk on this tomorrow at like 3 in the morning my time, so I'll be missing it. I teach tomorrow too, so I saw you're here, Andy. I'll be missing your talk too, unfortunately. Um, but yeah, she's a real expert on this. I generally tend to like what she writes. She's very sensitive to the philosophy of math and sort of the many aspects of mathematics, which includes mathematical practice. And she finds all that in Husserl. So I encourage you to check out her talk. So, okay, that's it for sort of what it is and how to do it. Let me now just I might actually end really early, we'll see. Let me just give you a few examples of this. And a prominent one is the theory of time consciousness. It's if you just flip through all of Husserl's writings, which would take a while, there's tens of thousands of pages. I think pictures like this would kind of stand out to you, and they've stood out to other interpreters. This is his famous example of time consciousness. So, this is one of Husserl's own diagrams. This is something I made. So suppose, I don't have, suppose I take a bottle or something, or in this case, a cup, and I'm turning it in my hand. And then there's a sort of time slice where it's halfway through the rotation, and I see this logo on the cup. Well, at that moment, it's not like an isolated event. I have some retention, some immediate memory of what's just happened, right? And there's many cases where it wouldn't be the current experience it was without these retentions. And then I have maybe some expectations of what's going to happen next, so protension. And those retentions are modifications of, these are called, when this is happening now, it's called a primal impression. So this retention is a modification of this earlier primal impression. This is a modification of an even earlier one. And these diagonal lines correspond to these transformations from primal impression into increasingly far back retentions. And there's a kind of similar structure for protension. And so there's a pretty big literature on this, both type 1 and type 2. There's people who are just trying to use the formalization, which includes Husserl, by the way. He used these pictures and talks in a very mathematical way about this, that are just trying to make sense of what Husserl says independently of how time consciousness might be implemented in the brain or our cognitive system or other artificial intelligence systems. So pure type 1 stuff. But there's also stuff that I will call type 2, where people are looking at an active inference account, let's say, of time consciousness and using formalisms that kind of bridge between the two. This is interesting. This shows the power of mathematics, right? By making the idea, we could have just said, there's these memories that kind of fade and there's these expectations that kind of go in the other direction. But by creating a diagram and describing it in this way, it's facilitated lots of interesting discussions. So there's debates about what is the topological and maybe geometric structure of time consciousness. And so this is a proposal from Banega, where it's sort of spherical. I couldn't tell you the details. And this is a very interesting example from I don't know if it's Eliza. I think Eliza's the way I would say it. She's here, I think. Ramos de Andrade, who we've communicated by email, and she's got it as an asymmetric inverted bicone, where this is the primal impression, I think. This is the retentional manifold. This is the protensional manifold. And they're both kind of, as you go far enough in the future, you have pretty indeterminate expectations, and similarly for the past, which is why it kind of contracts to these points. So these are interesting. This is an interesting discussion to have that is facilitated by mathematics. Just as in any other area, right? Mathematics allows you to say things more clearly and precisely than you would otherwise, and have debates, more precise debates than you could have otherwise, like this. So I think this really does facilitate. Husserl always thought, phenomenology is infinite tasks. It's supposed to be communal, collective, and we should be, working out the details. It's a fallible process. People make mistakes. And he thought the best way was for everyone to sort of collectively think about it. And mathematics facilitates that. And I think this is a good example. A second example is from my own work. This is a book I wrote in 2016 on Husserlian phenomenology. in the book, this is all type 1 phenomenology. I'm very much a type 2 person. I've got interest in neurophenomenology. But in the book, I restricted myself to just let's make sense of what Husserl says and try and say that as clearly and formally as possible. And I describe these two rules, which Mark will also be talking about a little. And the first, this is meant to capture things like constitutive phenomenology, the theory of horizons, some of the stuff on time consciousness. And the first is this expectation rule. And the idea is suppose you're in an environment, you've got some background knowledge K, you're looking at, say, a house from the front, a classic Husserl example. And so that's some, little v and v. You've got some little k and k, little v and v. And then there's what you can move in different ways, which is this sort of kinesthetic experience. And let's say I move to the right of the house. And when I do that, at the moment I do that, I am going to now have a set of expectations about what I will see next. These are not explicit expectations, they're implicit expectations. They're sort of counterfactual in the sense that certain things would surprise me, other things wouldn't. The ones that don't would fulfill my current implicit expectation. And so that's a mapping from V to 0, 1, where the higher the number here, the more fulfilling the subsequent experience, visual experience is. And this is basically like a probability distribution over subsequent visual experiences. And I'm just trying to capture, Husserl describes it very much like this. So yeah, so I'm here, I take some motion B, that gives me this basically probability distribution over different visual experiences that each has a different level of fulfillment. And then this is now my subsequent experience, which was something I expected, so I experienced fulfillment. And Husserl says fulfillment is very dominant in everyday life. Right now, nobody's doing anything weird. Nobody's got to if somebody exposed their face and was wearing a dragon costume or something or dancing around crazily, that would surprise me a little. Everyone's doing things I expect. All morning things have happened. My breakfast burrito was heated up and did not explode or turn into some strange object. Fulfillment is pretty dominant in everyday life, and this kind of captures that. The learning rule is just saying that the same first three terms here, factors or whatever, and you say you take what you know, what you see, what you do, and then what you subsequently see, right? So this includes this updated, my subsequent visual experience, and then your background knowledge will be updated in such a way that when I go back and look at the same thing again, maybe this probability distribution is a little sharper. Whereas if the subsequent experience is not what I expected, so a frustration, like if it was, there was some holiday and people are starting to wear like weird costumes on the Zoom call, then I will update my knowledge and stop being surprised by it when Johannes explains what's going on. And so this is roughly a Bayesian kind of update rule, right? The distribution kind of moves around as things occur. And again, then I use these rules to explain or to formalize many different ideas in Husserl, and that's why I call it a unifying interpretation. It's independent of naturalistic considerations, but it's meant ultimately, I think it does facilitate neurophenomenological considerations. So it's relevant to type 2. And then a plug for Mark's talk, he's going to be describing these as type signatures and then saying, look, one of the virtues of this is that it allows for the formulation of alternates, just like we saw in the last slide. So he's got some alternates to these and some other proposals. And so again, it sort of facilitates this Husserlian idea of ongoing communal work in phenomenology. I think you'd be happy to know 100 years later it's happening. Okay, a few other examples. So mereological structures are an interesting one, sort of at any given moment. There's a lot of stuff happening in the field. I'm seeing things, I'm hearing things. There's questions about how these different parts link together. Mereology is itself a formal theory, but the mereology of a state of consciousness, a sort of field of consciousness, what some people have called a total conscious state, is interesting in that there's this kind of dependency between the parts, right? If you change one thing, it seems to have a pretty significant impact on other things. And how that dependence works is still not, I think, clear. And what kind of mereological story is appropriate to that is also unclear. And there's not a lot of work on this. There is Zoe Lee at UCLA is doing a little bit on this using sheaf theory, which is quite interesting, looking at sort of compatibility between experiences in different sort of domains of current experience. So interesting stuff here. This is one where there's a lot in Husserl and subsequent. So Husserl in Thing and Space talks about things like the cyclical manifold of turning, he calls it. So if you're in a stable environment, so you assume nothing's changing, then if you turn around in place, you should have a kind of periodic sequence of experiences, visual experiences, for example. That's just kind of how, our space works, right? If things aren't changing and you turn around, then you should come back to the same visual experiences over and over. I'm not going to talk as much about this as I'd like, although I'm happy to come back to it, but I think it's really interesting. So Husserl's got this whole eidetic phenomenology and this concept of free variation. And the big picture on this one is that, we could imagine, it's logically possible that sensory experience was completely fragmented and kind of chaotic. He talks about a maelstrom of sensation. You could just imagine like a pointillistic array of just random sensations. Maybe if somebody punched you in the face or under the influence of some drug, you had a little bit of this, but we could imagine it's kind of radicalized and everything's kind of going crazy. Well, then you wouldn't experience objects at all. You'd maybe be there and you'd have experience in some sense. It's hard to say, but certainly there wouldn't be kind of a stable world of things that behave as you expect and so forth. For there to be a world of things the way we see them, certain rules have to be in place, like the rules I just showed you, right? And I like to think of this like think of somebody like think of a graphics programmer. So, we could imagine like somebody wrote a very simple computer program for the screen, which just displayed a random value at every pixel location on your TV screen. Nothing would then appear on the TV screen. It would just be snow. So what a graphics programmer will do with the help of a lot of libraries is make it so that the way the TV screen does things, the way the video output works in response to different key and mouse presses is systematic in a certain way, right? So, if you're in a 3D environment in a video game and you go forward, then objects are going to, render as, larger in the 2D screen in front of you. So all those structures that the programmer has to put in are like the eidetic rules that Husserl describes. I think they're kind of what he had in mind. They're structures in virtue of which we see things at all. And they're kind of the implicit rules that govern the way things appear. And this is kind of the fundamental structure of reality. And at one time I was thinking of it like the structure of the program that runs the matrix, if you've seen that. Now I've been working on this a little. Mark and I have he's pressed back on this a little bit, I think with pretty good reason. Essences in Husserl are really these kind of logical, necessary things that you couldn't imagine being otherwise. And a lot of the examples I use in these graphics programs have a kind of contingency associated to them, which is more like an empirical generalization than what Husserl calls an essence. Here I'm kind of Aquinian, I guess. I think there's a kind of continuum and that a real strict essence is a kind of limiting case. And I may depart from Husserl a little in this regard, which I'm happy to do when necessary. Let the phenomena should be my guide, not just whatever Husserl happened to write. But it's a really interesting one. It is helped by formalization, and so it's another example. Now, I've focused a lot on Husserl, but there's many other examples in many other phenomenologists. I like to show this picture of this bibliometric study I did about, I guess, 5 years ago or so now, where we looked at all the different papers in the phenomenology literature in the database we had access to. And, each dot is a kind of paper or it's an author, sorry, and each link is a citation between authors. And then it ends up having this kind of community structure you could look at. My reason for this is actually another kind of indirect example of using a mathematical tool to understand the phenomenology literature, which enabled a lot of interesting questions to be asked. But my point here is just there's a lot out there and a lot of things that could be formalized. We could imagine formal analysis of Sartre's theory of the imagination, of Merleau-Ponty on optimal grip, of Heidegger on the ecstasies of temporality, which are so suggestive and interesting, all this stuff in Division 2. I don't think Heidegger would like having that stuff formalized, but that doesn't have to matter to us. If it's interesting and it seems apt and it's suggestive, I think of this as this big database, and we're now living phenomenologists, and it's up to us to make sense of it. And if mathematics is helpful to do that, then we should use it. So that's why it's good that Bamberg, good job, administrators at Bamberg for funding this. Okay, let me end by saying a little bit about computational phenomenology. This is a term that's been around. This is something else that Mark is going to be talking about. I think it's going to be focus of his talk. And this is kind of, you could call it a special case of mathematical phenomenology where the calculations are complicated enough that they really couldn't easily be done in one human being's mind. Husserl actually has a lot of interesting things to say about this. He talks about calculations, algorithms, and computations in the sense of machine implementations of algorithms. So he's got a bit of the ontology worked out, which is interesting, and thinks about it. I could talk a little bit about that if interested. But anyway, so it seems like this is just a special case of mathematical phenomenology, where the math is just particularly complicated and where a lot of it will be opaque to us just because it's happening inside this giant computer. Um, it's mostly used in type 2 settings, right? When we're doing these mathematical models, it's often to support, naturalized or neural phenomenology. But there's this question, could a computer model ever be useful to kind of pure phenomenology, what I call a type 1 setting? And Mark's doubtful, but open to it as a possibility. He's just not convinced. I think it might happen, and I'm going to give you an example that he's not convinced by. And it is maybe it's a tough one, but I'll run it by you and then we could talk about it. So it's this concept of a feature visualization in a deep neural network. And this is Google Net. It's a pretty old, I think this is over 10 years old now. And at the time, this was not a model of the human nervous system. It had an engineering intent, just better image recognition. And they weren't trying to model neuroscience or anything, certainly not trying to model phenomenology. They were just building this tool. It turned out later, it is a pretty good, models like this are pretty good at modeling the nervous system, but we could set that aside and just treat this as like a giant, like this would be very hard to do just using pen and paper, right? You had to have a computer implementation to do this and to see that it worked. And it did work quite well, these kinds of deep convolutional networks. And then these questions came up about what's happening in their interior layers. And there, I mean, the computer is doing something like recognizing objects in pixel arrays, which is something we do. You know, we look at things and recognize things, or something similar to what we do. And I think insights coming out of these do, in my mind, maybe shed light on phenomenological claims independent of neuroscience. And so what people started doing, and this is kind of the background to mechanistic interpretability research today, is try and figure out again what's happening in these interior layers. And they could use something called feature visualization, where you do gradient ascent on pixel space. So you say, all right, I'm going to look at one of these sheets, let's say. And I'm going to say, what image will maximally activate this channel here in this COM3 layer? And so you start with a random pixel pattern, and then you keep changing it in the direction of the gradient that makes this average activation in one layer maximal. And in this way, you can get these pictures of the preferred inputs of different layers. You could do this for whole layers. You could do this for single units within layers and for other things as well. So it's a pretty flexible tool. Now, at the early layers, you get things like edges. This is the extent of my PowerPoint abilities. This took me quite a while just to do that much. So, patterns like this will produce a lot of activation at earlier layers. I think actually this is in the COM2 layer. And then this is maybe in COM3, you get these more texture-like things. And then at this is, I think, mixed 4. It's one of these layers. You get even more complicated patterns. And now Husserl talks about, this is an analysis of passive and active synthesis. He talks about edges and he says, there is this kind of sensory hyletic dimension to perception, and there is a structure to things like edge detection. You're aware of edges. When you look at something, you're aware that thing has a hard edge, that thing doesn't. That does seem kind of like an originary intuition in his sense. And it does seem to have a structure, right? Things will tend to the color gradient will change kind of rapidly when that happens. And there is this intuition that edges maybe somehow form into textures somehow, and surfaces and into more complicated things. And I look at this and it's like, well, yeah, maybe something like I'm seeing some fuzzy ballish thing or some interleavedness thing when I'm looking at different patterns. And that's just a sense I have that allows me to compare the thing I'm looking at to other similar things. And I just don't think, I mean, it's hard to make this effable, right? This feels pretty ineffable, but this thing does kind of F it, EFF it. Like maybe this is it. Maybe that's something I'm seeing. It just feels kind of plausible. And then this is now, this is a deeper layer. And so this is now showing single neurons now that are preferred inputs for single neurons for something like this kind of stripy pattern that occurs both in baseballs and in these kind of lowrider rims and these tires and whatever this thing is here, maybe some corrugated plastic for running cabling. And it does feel like there's some stripy thing I'm seeing when I look at those things, such that if I see two of these things, I see a comparison, or if I saw just one of them, my mind might wander off to one of the others. This is like some cloudy tubular thing that you see that's activated both for contrails and pretzels and rope. And some cylindrical cloudiness seems plausible to me as some sort of hidden but still present aspect of our phenomenology. And kind of seeing how these work, seeing how they relate to these other layers, this seems like a case where really paying close attention to the algorithm, even independent of consideration of its link to neuroscience, could shed light on the phenomenology of early visual processing. So how far I can get with that, I'm not sure, but it's meant to sort of illustrate the possibility and again, create a little discussion and potential division between Mark and I. I'll stop there so we have plenty of time to take questions and have a discussion.